Video Lecture 10B, VSEPR Theory in Molecular Geometry. The overall geometry of a molecule mainly depends on the orientation of the sigma bonds and lone pairs around each atom that is bonded to two or more atoms. We can use VSEPR theory, the valence shell electron pair repulsion theory, to easily predict the geometry around any atomic center that has two or more bonds. Recall that VSEPR theory tells us that electron pairs will occupy positions that minimize their repulsion. We use this theory to predict the type of hybridization that atomic centers have. Therefore, we can group molecular geometries by their hybridizations. It is important to note that we are only considering the sigma bonds and lone pairs around each atomic center with two or more bonds. We do not treat or consider multiple bonds in this analysis. Also note that we can describe a geometry around any atom that has two or more bonds. We don't consider terminal atoms, which can only form bonds in one direction. The overall shape of a molecule will depend on all of the molecular geometries around each atom in the molecule with two or more bonds. Our first group are molecular geometries for sp hybridized atomic centers. If an atom forms two sigma bonds and has no lone pairs surrounding it, its molecular geometry will be linear. An example of such a molecule is carbon dioxide. Note that we show a Lewis structure for carbon dioxide on the left and a ball stick model on the right, drawn by the molecular modeling program Avogadro. For molecules with sp2 hybridized atomic centers, we can describe two molecular geometries. The first is if the atomic center has three sigma bonds and no lone pairs. The molecular geometry will be trigonal planar, where all of the bond angles will be about 120 degrees. An example of a trigonal planar molecule is boron trifluoride. Note that in this example, we draw a Lewis structure on the left, a geometrically realistic structure in the center, and a ball stick model drawn in Avogadro on the right. We can also have a geometry in which we have two sigma bonds and one lone pair. This molecular geometry will be bent or angular. Ozone, O3, is an example of a bent molecule. Note that the central oxygen in ozone has one lone pair and two bonds. The lone pair will occupy one of the hybrid orbitals, while the others form sigma overlap with the two terminal oxygens. Although we can't see the lone pair in our ball stick model, we see its effect by the shape of the molecule. For sp3 hybridized atomic centers, we have three possible molecular geometries. The first comes when we have four sigma bonds and zero lone pairs. In this case, the molecular geometry is tetrahedral. Methane is an example of a tetrahedral molecule. We've encountered this before in our previous lecture. If an atomic center has three sigma bonds and one lone pair, the molecular geometry is trigonal pyramidal. Ammonia, NH4, is an example of a trigonal pyramidal molecule. Again, just like before with the bent example, one lone pair occupies a hybrid orbital, while the others form sigma bonds with the hydrogen atoms. Although we can't see the lone pair, we see its effect in the ball stick model on the right. Our final example in this group is atoms with 2 lone pairs and 2 sigma bonds. This gives rise to a bent geometry. This is similar to the bent geometry we see for sp2 hybridized atomic centers. However, the bond angle will be about 109 degrees, about 10 degrees smaller since it's caused by the presence of 2 lone pairs instead of 1. Water is our favorite example of a bent molecule. Note that the 2 lone pairs of water occupy 2 hybrid orbitals, while the other hybrid orbitals form sigma bonds with hydrogen. The sp3 hybridization, as well as sp2 and sp, are very common hybridizations in general chemistry and in organic chemistry. You will be asked to specifically memorize these molecular geometries that correspond to these hybrid orbitals. The next 2 groupings are less common in general and organic chemistry. However, we will mention them anyhow. These are the molecular geometries for sp3 dehybridized atomic centers. If the molecule has 5 sigma bonds and no lone pairs, the molecular geometry will be trigonal bipyramidal. An example of a molecule with this geometry is phosphorus pentachloride. If a molecule has 4 sigma bonds and 1 lone pair, the molecular geometry will be seesaw, or a distorted tetrahedron. Sulfur tetrafluoride is an example of a seesaw-shaped molecule. Note that one of the sp3 dihybrid orbitals are occupied by a lone pair. If an atomic center has 3 sigma bonds and 2 lone pairs, the molecular geometry will be T-shaped. Chlorine trifluoride is an example of a T-shaped molecule. Note that 2 of the hybrid orbitals are occupied by lone pairs. Finally, we can have a linear geometry once again if a molecule has 2 sigma bonds and 3 lone pairs. Xenon difluoride is an example of a linear molecule. Note that the xenon atom has 3 lone pairs around it in hybrid orbitals. This is what gives rise to the linear geometry. Our final grouping are the molecular geometries for sp3 d2 hybrid orbitals. If an atomic center has 6 sigma bonds and no lone pairs, the molecular geometry will be octahedral. Sulfur hexafluoride is a good example of an octahedral molecule. If an atomic center has 5 sigma bonds and 1 lone pair, the molecular geometry will be square pyramidal. Iodine pentafluoride is an example of a square pyramidal molecule. Note that 1 lone pair occupies a hybrid orbital that is below the plane of the molecule. Finally, we can have an atomic center with 4 sigma bonds and 2 lone pairs. This will give rise to a square planar molecule. An example of a square planar molecule is xenon tetrafluoride. Note that the lone pairs on the xenon atom occupy the hybrid orbitals above and below the plane of the molecule. Now we will practice assigning molecular geometries and hybridizations to atomic centers and molecules. For the following 4 molecules, we will predict the hybridization and the molecular geometry for each ball-faced atomic center. Okay, we're going to predict the hybridization and molecular geometry of 4 molecules. The first molecule we'll look at is HCN, hydrogen cyanide. Whenever you're predicting the molecular geometry and hybridization of a molecule, you first need to draw a valid Lewis structure. This will allow you to locate the bonds and lone pairs around each atom center. This is the Lewis structure for HCN. We're only interested in the geometry around the carbon atom, since it is bonded to 2 other atoms. If we examine this carbon, we note that there are 2 bonding domains. One single bond between the carbon and the hydrogen, and a triple bond between the carbon and the nitrogen. Triple bonds don't typically, or the pi bonding electrons do not typically contribute very much to the molecular geometry. Therefore, we only need to consider the sigma bonds and lone pairs around each atom center. Carbon, therefore, only has 2 sigma bonds. If we refer to our molecular geometry chart, if an atom has 2 sigma bonds and no lone pairs surrounding it, the geometry is predicted to be linear. A linear molecular geometry corresponds to sp hybridization. It is also useful, in addition to looking at the Lewis structure, to look at a molecular model. Here's a molecular model of HCN. The white atom corresponds to the hydrogen, the black atom represents carbon, and the blue atom represents nitrogen. Notice that the triple bond linkages. It's very clear to see by looking at this molecular model that the molecular geometry around the carbon atom is linear. This keeps the electron pairs, the sigma bonding electron pairs, as far apart as possible. Our next example is NO2-, the nitrite ion. Here's the Lewis structure for the nitrite ion. Again, we're only interested in the nitrogen atom, since it's the only atom that has more than 2 bonds. Notice that the nitrogen will have 2 sigma bonds, but it also has 1 lone pair. A total of 3 electron groups. According to our chart, an atom that has 3 electron groups will be sp2 hybridized. The sp2 hybrid orbitals will adopt a trigonal planar geometry. However, the molecular geometry will be bent or angular. Again, it is very useful to look at a molecular model. So here's one for the nitrate ion. Here's our central nitrogen and the two oxygens. Note that the molecule is bent. The lone pair is sticking off of the central nitrogen in a vertical direction. The presence of that lone pair repels the two bonding groups of electrons so that it adopts a bent geometry. Our next molecule is a bit more complex. This is the methanol molecule. Its Lewis structure is as follows. Note that we have two atoms that are bonded to more than two other atoms. We have a carbon and we have an oxygen. We can describe a unique geometry around each atom, both of which will contribute to the entire geometry of the molecule. For carbon, we notice that carbon has 4 single bonds surrounding it. This will correspond to 4 sigma bonds. There are no lone pairs on the carbon atom. The 4 sigma bonds would correspond to 4 electron groups, which would give us an sp3 hybridization. Since all of the electron groups correspond to bonding groups, the geometry will be tetrahedral. We can also describe a molecular geometry around the oxygen atom. Oxygen is participating in 2 sigma bonds. But it also has 2 lone pairs. This is a total of 4 electron groups. This also corresponds to sp3 hybridization. However, since 2 of those electron groups happen to be lone pairs, the molecular geometry will be bent. Once again, it is very easy. It is easier to look at a molecular model of our molecule. So here's methane. Here's the carbon atom around methane. Here's its 4 sigma bonds, and they adopt a tetrahedral geometry. Each one of these single bonds is pointing to the vertices of the vertex of a tetrahedron. Here's the oxygen atom. Notice that it takes on a bent geometry. The two lone pairs on the oxygen are causing the two sigma bonds to be in the bent configuration. Our final example is the bromine tetrafluoride ion. Which has the following Lewis structure. Again, we are only interested in the bromine since it's the only atom in this molecule that forms two or more bonds. Bromine is forming 4 sigma bonds in this molecule. And it has 2 lone pairs. A total of 6 electron groups. If we look at our chart, this corresponds to sp3d2 hybridization. Our sp3d2 hybrid orbitals will adopt an octahedral geometry. However, since 2 of those orbitals will be occupied by lone pairs, the molecular geometry will be square planar. Again, we can look at a molecular model to really get a feel for the geometry. Here's a good molecular model for the bromine tetrafluoride ion. Notice that the 4 bromines adopt a square planar geometry with bond angles of 90 degrees. The lone pairs would occupy the space above and below the plane of the molecule.